Electrostatic fields. Electrostatic fields are found in the neighborhood of any distribution of electric charges. The electrostatic field E at any point is defined by the relation the limit of the charge as it approaches zero, function of the force over the charge, where F is the force that would act on the test charge if it were placed at that point. It is necessary to define the field as the limit of the force to charge as the test charge approaches zero only because a finite test charge may change the distribution of neighboring charges, especially if these reside in a conductor. The simple definition of the field is valid for any size of test charge provided the charge producing the field are not displaced by the presence of the test charge. The definition states that the electric field is a vector that points in the same direction as the force vector when the test charge. Note that K is equal to 1/4 pi, which is 9 times fields by direct integration. While equation 2-2 is useful only for calculating fields due to distributions of point charges, it can be expressed in the form of a vector integral for use in calculating fields due to continuous distributions. Just as a scalar integral can be considered to constitute an algebraic summation of infinitesimal scalar elements, a vector integral constitutes a vector summation of infinitesimal vector elements. In figure 2-8, charges are smoothly distributed within the irregular volume T, and it is desired to calculate the electric field at that point P, whose coordinates are x, y, z. A small element of volume, dt, located at x, y, z contains the charges where vector mathematics for electrostatic fields. Field calculations. The electric field at all points in space due to any particular distribution of point charges can be calculated by direct substitution into equation 2-2. To obtain such a general expression, the point P at which the field is calculated is given by the general coordinates x, y, z. Each of these charges in the distribution contributes one term to the summation. Its particular magnitude and its particular coordinates are substituted into that term. If many charges are involved, the expression is too long to be practical. Fortunately, simpler methods can be developed for calculating fields in most actual problems. However, since the simpler methods are based upon the fundamental law expressed in equation 2-2, its implications should be mastered. The calculation of the field at some particular point due to 2 point charges should help to clarify this law.